Welcome to a new video of heat transfer. Today we study the log mean temperature difference method, also called LMTD method. That's useful to design heat exchangers. In particular, this method is used when the mass flow rate of the hot fluid and the mass flow rate of the cold fluid are known, and also when the four characteristic temperatures of the heat exchangers are also given. These are the inlet and outlet temperature of the hot fluid and the inlet and outlet temperature of the cold fluid. So the objective for this kind of design is to select a heat exchanger that satisfies these conditions. So therefore, we need to find AS, so the size of the heat exchanger. So to study the log mean temperature difference method, we study the balance, heat transfer balance between the two fluids. So in this schematic, we have the simple case of a parallel flow heat exchanger. The hot fluid loses heat to the cold fluid, so the temperature of the hot fluid decreases from the inlet temperature to the outlet temperature, whereas the temperature of the cold fluid increases from the inlet temperature to the outlet temperature. And we define delta Q as a differential amount of heat exchange between the two fluids. We also call delta T1 the jumping temperature between the inlet temperatures, and delta T2 the jumping temperature at the exit. Q, the heat exchange between the two fluids, is equal to U times A times delta TLM, where U is the overall heat transfer coefficient, AS is the surface temperature of the heat exchanger, and delta TLM is the log mean temperature difference that we need to find. So there are two useful relationships that arise from energy balance. So that's a Q lost by the hot fluid, and MH, mass flow rate times specific heat capacity times delta T of the hot fluid, and that's equal also to Q, and that's the heat gained by the cold fluid. So the M dot, mass flow rate of the cold fluid, times specific heat capacity CPC, and the delta T between the outlet and the inlet of the cold fluid. So if we set these two quantities to be equal, the heat transfer to be equal, this means that all the heat that's lost by the hot fluid is given to the cold fluid, so it's a conservation of energy, and therefore there are no losses of energy to the environment. The differential heat that's lost by the hot fluid, delta Q, is given by this expression, and that's equal to delta Q that's gained by the cold fluid. So we can rearrange and solve both expressions by the differential temperature dTH, dTC. We take the difference of these two expressions, we find this differential expression, but we also know that delta Q dot is equal to U delta T dAs. So we have nothing here but take the differential of the expression that relates Q and U. So delta Q, we found a special delta Q, we can substitute it here in this expression. So we eliminate delta Q. We arrive at this expression here. Now we can move the delta T to the left-hand side. So on the left-hand side, we just have the delta T between the hot and the cold fluid. And now we can integrate. So we have a natural log here because we have dt over dt over T. By integrating between the jumping temperature at the outlet and the jumping temperature at the inlet. We substitute these two delta T's and we find log expression. And to proceed now, we need to eliminate the m dot for the hot fluid and the cold fluid, the mass flow rates and also the specific heat capacity. We do that by using the expression of the Q. We substitute in there, and we can see that the Q can be simplified in this way. So a bit of algebra. So Q appears here at the numerator. The numerator can be simplified. So we have the log of this ratio, which is also equal to an expression that contains the 4 temperatures at the inlet and outlet of the cold fluid, the hot fluid, divided by what we need to find, the delta T LM, log mean temperature difference. If you remember in the figure, we defined the delta T1 and delta T2, the jumping temperature at the inlet and at the outlet. So we can introduce this into the expression and we solve for the log mean temperature difference. And we can see this is an exact representation of the change in temperature in a heat exchanger. And what's important to note here that the delta TLM depends on all the 4 temperatures of the heat exchanger. So the 2 inlet temperature, so the hot fluid and cold fluid, and the outlet temperature of the cold fluid and the hot fluid. What's important to remember in heat exchangers is that the delta TLM for a cross flow is always larger than the delta TLM for a parallel flow. So a cross flow is always larger than the parallel flow. Therefore, if you're given the Q that we need to exchange between the 2 fluids, it's a good idea to use a cross flow heat exchanger because a smaller surface will be required. And therefore, we can save space, money, and also energy. Now we have found the log mean temperature difference in idealized case. So the case in which the flow is in cross flow or parallel, but in general we have more complicated heat exchangers. So the question is, how do we find the delta TLM in more complex scenarios? What we do, we use a correction factor. So the delta TLM of the heat exchanger of choice, it's equal to F, the correction factor, times the delta TLM in the cross flow situation that we just saw before. So all we need to do, we need to use the 4 temperatures that we have, the 2 inlet temperatures, the 2 outlet temperatures, and we find the delta TLM as if the heat exchanger were in cross flow in the idealized case, and then we multiply by F. So F depends on the geometry and also depends on the 4 temperatures. So how do we find F? So remember, F represents the deviation from the idealized case of the cross flow. The best way to find F is also a quite quick way, is to use charts. So you find in all the heat transfer books charts of this kind. So F is on the y-axis and the quantity P is on the x-axis. And then we have different pink lines here, and each line represents a different value of R. So this chart is for one shell pass heat exchangers, but you have different charts for different heat exchangers. So for one shell pass, then we have T1 and T2 in capital letters. Then this represents the inlet and outlet of the flow flowing this way, and small t1 and small case t2 are the inlet and outlet of the other fluid. So once we are given these 4 values, we can compute P, so we know where we are located on the x-axis. And then what we have to do, we have to move up until we reach the pink line of interest. And how do we compute the pink line? Well, we have to compute the value of R. So once we have the location that we want, you just move on the left and we find F, and we note F is always smaller than 1, and this is correct because we saw before that the log mean temperature difference for a cross flow is always larger than the log mean temperature difference for another heat exchanger. Thank you very much. I'll see you in the next lesson.